Hello, in this video, I will introduce TS quality. I will start by introducing the overview of our work, including the background, existing works, and our contributions. Then, I will show you the system architecture. At last, I will demonstrate our system, presenting how to measure time series data quality in Apache IOTDB, and how to integrate with Apache Superset and Zeppelin for complements. Time series has been found with various data quality issues, such as completeness, consistency, timeliness, and validity, especially in the scenarios of IoT, Internet of Things. Analysis upon dirty data without prior assessment of data quality may yield misleading results. Thus, it's highly demanded to have an overview of the data quality issues on the millions of time series stored in the database. For example, this figure presents a segment of time series with 4 types of data quality issues. As shown, the data points are usually collected every minute, a preset frequency of sensors. A point, however, is missing at time 1:02 p.m. and leads to completeness issue. In contrast, the point at 1:06 p.m. is retransmitted, resulting in a redundant one, known as consistency issue. Moreover, a point could also be delayed. For example, the one that should appear at time 1:04 p.m., but not until 30 seconds later. Such an issue is measured by timeliness. The validity measure is evaluated with respect to a set of constraints on both time and value. For instance, the two horizontal red lines, Vmin and Vmax, denote the valid range of values. The point at time 1:08 p.m. has an abnormal value smaller than the minimum. In addition, the two red arrows Smin and Smax specify the speed of maximum and minimum value fluctuation over time. The data point at time 1:01 p.m. has a value fluctuation greater than Smax, and thus has abnormal value as well. Existing systems, such as Cleanis and CleanTS, propose to clean the dirty data in individual time series. However, commodity databases often store millions of time series for thousands of devices. There is still a lack of overall assessment for all the data stored in the database. Moreover, such works are not well integrated with the ecosystem. In this demo, we present TS quality to measure data quality in Apache IOTDB, an open source time series database developed based on our preliminary study. In IOTDB, each time series consists of a time column and a value column. For timestamp issues, we consider missing, redundant, and delayed points. For the value column, we investigate abnormal values with respect to range, variation, speed, and acceleration. The major features of TS quality are of 3 aspects: well-integrated ecosystem, interpreted results, and customized measures. The system architecture of TS quality is shown in this figure. As we can see, TS quality follows a 3-tier architecture model: storage, computation, and interface. The interface layer at the top is responsible for direct interaction with the user. It receives data quality SQL queries, visualizes the results in the form of graphs, such as line charts and scatter plots, and returns them to the user. Specifically, users can choose TS Quality Dashboard, IOTDB's native visualization tool, which gives an overview of data quality at the time series level, as well as a detailed anomaly analysis to locate and fix data quality problems in the data. TS quality is also tightly integrated with the open source ecosystem by interfacing with Apache Zeppelin for custom time series queries and Superset for the overall data profile. The computation layer reads the original time series data from IOTDB, calculates the number of all kinds of data quality issues in each time series, and stores the statistics in SQLite. The bottom layer in Figure 2 is the storage layer. IOTDB stores the time series data in the form of TS file and we use SQLite, a lightweight relational database, to store the results of the computation layer and provide information for the interface layer. Now, I will demonstrate the usage of TS Quality Dashboard. It offers a web view interface for users to view the data quality of one time series. As you can see, this is the home page of TS Quality. The 4 bold numbers in the top represent the number of data points, time series, devices, and databases respectively. The radar chart here displays the overall data quality of all the data in IoTDB, including 4 data quality metrics: completeness, consistency, timeliness, and validity. This bar chart presents data sizes of different time periods. As we can see, there are a total of 10 months of data in IoTDB, with November 2014 having the most data. Scrolling down, and we can see the data quality for each of the different time periods mentioned above. For example, the values of the 4 data quality metrics. We can also convert it to a line chart by clicking the button in the upper right corner and restore it. The table at the bottom shows all the history of data quality analysis of IoTDB using TS Quality. We can click on the Create button to create a new data quality analysis task. In this dialog, we can choose whether to read IoTDB data in a streaming way or using Spark batch processing. The number of samples here represents the number of points that TS Quality will plot in the subsequent presentation of the original time series data distribution. We can choose to calculate all 4 data quality metrics or only part of them. In this tab of the data source configuration, we can fill in the address of IoTDB and other information such as username and password. There is also an option to store the analysis results into PostgreSQL or Oracle. Then, we need to specify the time series path to be analyzed and the time range of the data. After that, there are some configurations for calculating the 4 data quality metrics, such as whether to consider null values when calculating completeness, whether to consider special values, and so on. In the configuration page of validity, we can specify the range of values for different anomalies. After the configuration is complete, click the Run button in the upper left corner to start running the analysis task. Refresh the page, and we can see that the task is running. To save time, we can directly view the results of previously completed tasks. This is the analysis result page. The 2 bar charts on the left show the data size and data quality for this time series aggregated by day, respectively. The 4 bar charts on the right give the distribution of the 4 data quality metrics values. As we can see, completeness is the lowest of the 4 metrics over the 6 days, followed by timeliness and consistency. And validity is the highest. The table at the bottom of the page gives the specific values of the 4 metrics for each day. We can filter the result according to different ranges of metric values. The Enter button on the right of each row can lead us to the detailed page of the analysis. In this page, the table at the top records the statistical information of the current time series, such as the average and maximum values. The 5 columns of the table represent 5 sequences: the original time series, the time info, the value variation, the speed of value variation, and the acceleration. Clicking on these 5 table headers, and we can see the distribution of values for these 5 sequences. The scatter plot at the bottom of the page gives the sampling of the original time series, and we can zoom in and zoom out of these 2 diagrams by dragging the cursor. The top menu gives us the access of the detail page for each of the 4 data quality metrics. For example, in this detail page of validity, the table at the top gives all the validity anomalies points, including value anomalies, variation anomalies, speed anomalies, and acceleration anomalies. The 2 red dashed lines in the bar chart below gives the constraint range of values. Points with values out of this range will be considered validity anomalies. The line chart below marks the anomaly point in the original time series and gives the possible repair. We can click on the repair label in the upper left corner to compare and analyze the original series with the repaired ones. The detail pages for other 3 data quality metrics are similar, each giving a list of the corresponding type of anomaly points and their fixes. Next, I will show you how to measure IOTDB data quality in Superset. Here, we can create a custom dashboard to view the overall data quality of all time series in IOTDB. For example, this dashboard gives the total number of time series and the total number of data points in IOTDB. The radar chart gives the data quality of all the data, and the pie chart shows the number of non-empty time series in IOTDB. The 2 bar charts at the bottom of the page give the data size and the data quality by time period respectively. The information about IOTDB now presented in Superset all comes from the calculation results stored in a relational database, which is calculated by TS quality. We have now completed the development of the connector between Superset and IOTDB, which can further facilitate users to analyze IOTDB data quality in supersets in the future. In Zeppelin, we can input custom queries to interact directly with IOTDB. For example, this SQL queries the data quality of one time series in IOTDB using 4 functions. The first parameter of the function is the name of the sensor in the time series path, and the second one specifies the window size when reading the original time series data with a sliding window for calculation. Users can select different chart tabs to display the query results, and hover the cursor over the line chart to examine the specific values of the 4 data quality metrics. The biggest advantage of Zeppelin is the ability to analyze time series data in IOTDB quickly and in real time, such as viewing all time series in IOTDB, displaying the original time series, and so on. This is the end of my demonstration. Thanks for watching.